So let us continue with this same thing. So what we are doing is looking at this parity check matrix over F4 and trying to find some code words just to get used to the arithmetic and also getting used to the idea of codes over F4, okay, non-binary codes. Okay. So let us say I put my message bits as say 0 1 0. Okay. If I do 0 1 0, it is particularly easy, right. So I have made two other multiplying factors as 0. So M2 simply picks up the second column, which is 1 and alpha. So P1 and P2 become 1 and alpha. Okay, so that is another code word in this code. Okay, so another one I might want to pick is say 0 0 1. If I do that, I would get 1 alpha square. Okay, so let us try something a little bit non-trivial. So let us say we do alpha alpha 1. Okay, right. So all that is fine. So a couple of definitions which I have to extend are Hamming weight and Hamming distance. Okay, so remember in Hamming weight and Hamming distance for binary, what is the definition? Hamming weight is the number of ones. Okay, for non-binary, for F4 and all, Hamming weight will become number of non-zero entries. Okay, so that is the first extension. So let us just do that real quick in this next page and then come back here. Okay. So if you have a vector v belonging to Fqn, okay, so where q is some power of prime, prime power as they call it, okay, the Hamming weight of v is defined as number of non-zero entries in v. Okay. So I am sure it is a very more precise way of writing it, but I guess it is clear. Okay. So whenever for binary you count the number of ones, in non-binary you count the number of non-zero entries. Okay. So if you have let us say u and v, there are two vectors in Fqn, the Hamming distance between u and v is defined as the Hamming weight of u minus v. Okay. So I have to say minus here because I am thinking of a general field. Okay. In what case will minus be the same as plus? Yeah, 2, when q is even, right. So when you have an even numbered field, power prime has to be definitely 2, and in that case minus can become plus, otherwise I have to say u minus v. Okay. So basically if you want this in words, it is the number of places in which u and v differ. Okay, that remains the same, it is the same as the binary case. Okay. So that is the formal extension of Hamming weight and Hamming distance from binary to arbitrary finite fields. Okay. So let us go back to these examples and try and answer the question of Hamming weight and the distance between two vectors. Okay. So the Hamming weight here is 0. What is the Hamming weight of this? 3. So is the Hamming weight here. So is the Hamming weight here. Okay. What is the Hamming weight of this? 5. What about distance between these two? 3, right. So distance between these two, 3. Okay. So you can find it out. Okay. So it is a simple enough definition, so it works. Okay. So I can give you other examples, but I think that should be enough, that one example will give you an idea of how these codes work. So now if I have an NKD code, if C, so let me just write that down, this is the definition for codes. Okay. So if somebody tells you C is an NKD code over Fqn, okay, So, we had this before for the binary case, right. You had an NKD code over F2n, okay, binary code of length n. What does this actually mean? This will be a k dimensional subspace of Fq n. Remember, Q has to be a prime power. If it is not a prime power, then there is no such field and it does not make any sense. Okay, Q has to be a prime power. So, it is a subspace of Fqn. Okay. And how is this subspace specified? Using our idea of two different matrices. Okay. So, you will have a generator matrix k cross n. So, the C will also be the row space of a k cross n generator matrix G. Okay. It will also be the null space of a n minus k cross n parity check matrix P H, sorry. Okay. But now this G and H will have entries from what? From Fq. Okay, that is the other modification. Okay, so these will be matrices with elements from Fq. Okay, but I should remind you once again that the Gaussian elimination operation works eminently over any abstract vector space defined over any abstract field. Okay, once you have the operations for the field, you can do Gaussian elimination on G. And remember, we allow for column swaps when we do Gaussian elimination, right. So, because we consider that as an equivalent operation as far as coding is concerned, does not change the distance, does not change the weight, does not change anything else, only changes the order. Okay. So, what you can do is you can start with G and H and do row operations basically the Gaussian elimination operations and column swaps and end up with what is known as a systematic version. So, that G becomes IP and H in this case, you can go back and check this, will become minus P transpose Ni. Okay, in the general case, if I know minus 1 is not plus 1, okay, Q could be odd, in that case it becomes minus P transpose I. Okay, you can go back and check the way I derived it, the minus will come, I would have swallowed it and I said plus because it was binary. If your characteristic is not 2, you have to carry over that minus, you can't kill that. Okay, so it will be minus P transpose I. You can check very quick, this I will be Ik, this will be I n minus k, okay, and you can check very quick that G H transpose will be equal to the 0 matrix, k by n minus k 0 matrix. Okay. So, you can do all the previous things that we did, there is no problem. So, you can think of a code word C as consisting of a message part which is k bits, k symbols, k elements from, so I should say what this is, I should be careful, I cannot say k bits, right, I should say k symbols from Fq. Okay, and then a parity part P which contains now n minus k symbols from Fq. Okay. This m is my free variable, so to speak, I can pick m as anything I want. Okay, and then I can use either the generator matrix G or the parity check matrix H and construct the parities as m times p. Okay, so I will get the parities very easily. Okay, so this sorry, m times capital P, should be careful. So, the small p equals m times capital P, right. So, that is the idea. Okay. So, this theory extends without any problem. The last so n and k are easy once again. So, D is the next definition, okay. D is the minimum distance, okay. The similar definition from before goes through without any problem, okay. So, you can do it this way, minimum for u v belonging to the code, u is not equal to v, the Hamming distance between u and v. Okay. But since we know C is a linear code, this becomes equivalent to doing minimum u and C, u not equal to 0, the Hamming weight of u. Okay. This becomes the same just by the same proof. Okay. So, this is the same as Hamming weight of u minus v, and this u minus v also belongs to C. Okay. So, it is a linear subspace. So, minus v, u minus v, all these things will belong to the same C, and based on that you can write this very easy formula for D. Okay. So, in particular what happens is the relationship we had between the Hamming, the minimum distance and the columns of the parity check matrix, how they are linearly dependent, that carries over without any problem, except that you cannot say sum to 0, you have to say linearly dependent, because sum to 0 was worked in the binary case, it will not work for the general case. Okay. So, that is crucial. Okay. So, D also happens to be minimum number of linearly dependent columns of H. Once again, this is a very hard quantity to compute, like I said, it is one of those NP complete things. Okay. So, you can't compute, can't hope for an algorithm to quickly compute these things. Okay. So, it is a difficult combinatorial problem to solve. Okay. So, minimum number of linearly dependent columns of H. Okay. So, how did we prove it? The key element in proving it is, if u belongs to C and Hamming weight of u is w, then what does it mean? There exist w columns of H that are linearly dependent. Okay. How did I show this? It is very easy to show this. Yeah, all you need is HU transpose is 0. Okay. So, how do you show this? HU transpose is 0, and there are only W non-zero entries in U. So, it clearly picks out only W columns from H, and those W columns are linearly dependent. Okay. So, that is the idea, and this is also if and only if, because if you have W columns being linearly dependent, then what do? You can manufacture a U so that H times U transpose is 0. You scale those W columns suitably, make them 0, put the other things as 0, you get the same answer. So, it goes both ways. So, this is crucial in this proof. Okay. So, that kind of rounds out everything I wanted to say about codes over finite fields. Okay. Hopefully, it is clear. I do not want to do any more examples than this one. Maybe we will do just one more example, and then after that we will call it quits. Okay. So, let us do a slightly more complicated example maybe. Okay. So, let me just hunt for a example which is a little bit non-trivial. Okay. So, for that let us go to F8. Okay, remember the F8 table works like this: alpha squared, alpha power 3 which is 1 plus alpha, alpha power 4 which is alpha plus alpha squared, alpha power 5 which is okay. So, this kind of tells you the F8. Okay. So, let us construct a parity check matrix. Okay, I will give you a slightly more painful Okay, so I am trying to see if I should give you r equals 2 or r equals 3. So n has become, so maybe I will put alpha power 5 also just to make it a bit more interesting. Yeah, so let us do that. This is so sorry. Taking a terrible amount of time to write this. I am sorry for that. Just trying to make sure I do not make mistakes. Alpha power 6, alpha power 9, alpha power 12, alpha power 15. Okay. So of course you can argue I do not have to write alpha power 8, alpha power 10 and all that. What is alpha power 8? It is actually alpha. Alpha power 10 is alpha power 3. All those things I can write, but I mean it's just, I think it hides the form if I write that. Okay, so if I write it this way, you see the form very easily, right? So you see each thing. So basically the ijth element of H, if you want to write the ijth element, you can write it as alpha power what? Let me see who gives me. So I equals 1 2 3, ij equals 1 2 3, you can write it as
minus 1, j into I minus 1, I minus 1 into j.
J minus 1 because
Maybe 2j.
Oh, okay.
so j minus 1 should.
okay, you can write it like this. Okay, so just to give you this form, I kept it like that. Okay, it's okay. You can do it also mod 7. So here you can put mod 7 if you like, but it's okay. It doesn't matter. Okay, so this is the form. So let's try to find out parameters for this code. Okay, so giving you the parity check matrix, you have to find n, k, and d. Okay, so n is the easiest, right? Isn't n the easiest? It's basically a primary school problem. How can you count? Okay, so count that 6. K is at least a high school problem. Okay, so it's not so much primary school. You have to do Gaussian elimination. Okay, so what is k? So what is n minus k? Okay, so you have to do Gaussian elimination before you can be sure, right? So the first 3 columns are enough. Okay, I know ahead of time that the first 3 columns are linearly independent, so you can do with that, and then you will show that the I can be formed there. Okay, so it's a good exercise to try that. Okay, I'll urge you to try it at some point in time. Go back home and try that. So you can do the combination. The first operation you do will be what? Second row equals second row minus the first row. Okay, minus is the same as plus. Remember F8. Okay, so you do second row equals second row plus first row. So you get a 0 there. Okay, and then you get other elements. Likewise, you do third row equals third row plus first row. You will get 0 plus 0 and all these other elements. And then you come back here and then you divide by whatever you had there to make that 1. Then you subtract. Just do the same standard Gaussian elimination, except that your operations are with this field. Okay, the field that I have written down here. It's not with anything else, you know. Okay. Okay, so you will get n minus k to be 3, and this will imply k is 3. Of course, the interesting question is, what is the interesting question? Minimum distance, right? So that's the most interesting question. Okay, first tell me about an upper bound. What is the maximum minimum distance that you can have? Okay, singleton bound is something you can use. Okay, the other bounds are a little bit more difficult. For the small cases, singleton bound you can use. What does singleton bound tell you? D is less than or equal to 4, right? I never showed that the singleton bound also holds for FQ. Okay, you can go back and do the same proof that I did before. The exact same proof, that pigeonholing type of argument with k minus 1 will carry over, and you will get n minus k plus 1. Okay, so 4 is the distance that is possible with this. Okay, you cannot have anything more than 4. Okay, I can easily find a code word of weight 4. All right, You do the Gaussian elimination, you can find a code word of weight 4, yes or not. Okay, see, remember, if you do Gaussian elimination, what happens? Think about this. This is fairly important because you are going to get I3 and then you will get several rows, maybe some row here, I do not know what this is, some H4, so on you will get. Okay. Now, this is a message bit, message symbol, which I can pick to be anything non-zero, and then I pick everything else as 0. Okay. Then what is the maximum weight that I can possibly have? This 1 plus this 3. Okay. So, 4, I can easily find 4. Okay. Alright. Now, after you have reduced it to I3, you can look at each column. Okay. There are 4 entries in 3 entries in each column, sorry, and if any one column has a 0 entry, what does it mean? A 0 entry, one of the entries in some column is a 0, then can I have a weight 3 code word? You are not able to visualize this. So let's see an example. Okay, so then you can visualize what's happening. Okay, so it's a very subtle thing, but it's important to know what's happening. See, remember, you can do Gaussian elimination and get 1 0 0 and 0 0 1, right? And then I have some additional columns here which I would have got after the Gaussian elimination. I don't know what it is, but if all 3 of them are non-zero, then if I put some non-zero entry here, I will have a weight 4 code word, right? So remember, I have several other columns also. Okay, if I put zeros all here and I put some non-zero entry here, something non-zero here, then I will, and if all these 3 are non-zero, I will definitely get a non-zero entry here. So, I will get a weight 4 code word. If it turns out that this column already had a 0 after I did the Gaussian elimination, what will happen? Clearly this one will not appear at all, right. So, even these 3 guys are linearly dependent. Okay. So, I put something non-zero here, put all zeros here, this guy will not play a role, this will continue to be 0. Okay. So, I get a weight 3 code word, this is weight 4. Okay. Is this kind of roughly clear? Maybe not. Okay, let us see a more concrete example. If I have a parity check matrix like this, let us say alpha, alpha squared, alpha power 3. Okay. So, this is suppose my parity check matrix. Okay. Let us do NKD for this. Okay, it is a very easy matrix to do NKD. Okay, let us say N is 4, K is what? K is 1, okay, and what is D? See, remember, this is a parity check matrix. What is my message bit? Message symbol, there is only one message symbol, okay, and then I have 3 things, okay, yes or no, 3 parity symbols, okay. So, if I put anything non-zero, if I put m equals 0, what do I get? M1 equals 0 will give me the all 0 code word. If I put M1 as anything non-zero, what will I get for P1, P2, P3? Can I get any one of them to be 0? No, because it's alpha times M1, alpha squared times M1, alpha power 3 times M1. Clearly, if M1 is non-zero, none of these 3 guys can be 0. So, from there you see immediately D is 4. Okay, you understand? Okay, it is very simple to see that. Okay. Now, in case instead of this alpha squared, suppose I had 0, 3. Okay, so you would get D equals 3. Do you see that? So, the same point I am making here in the more general case, even when you have other columns, other more messages, because it does not matter, you can make all of them as 0, even if you have one column, then it becomes 3. Is it okay? Think about it, that is an interesting way of finding out minimum distance, which might help you sometime in the future. Okay. So, you might want to apply something like that here, but it is still a little bit more confusing, you know, I mean, you have to check very carefully, you do not know if it works or not, right. You have to check all possible combinations here to find out the minimum distance, okay, or you have to be very smart and you should know some very fancy methods to find the minimum distance. In fact, you can show, I believe, that this minimum distance here will be equal to 4, okay, for this parity check matrix. It is a little bit non-trivial, but anyway you can show that for this parity check matrix minimum distance will be 4. You can basically show any 3 columns that you pick from this parity check matrix, they will be linearly independent. You can show that it's a very standard construction. If you construct like this, you can show that this is true. So you will have d equals 4. So that's the idea here. Okay. Anyway, that's the only other example I wanted to do. I know I didn't do a very complete job of doing with this example, but hopefully this gives you enough idea of the kind of things that are involved here. Okay, so it's not very easy. Okay, so even for finding k equals 3, you have to do some work. It's not as trivial as the binary case when you have to do some Gaussian elimination carefully, otherwise some crazy things can happen. Okay. All right. Okay, but go home and try this. Okay, so do the Gaussian elimination and check that every column has completely non-zero entries. You will see that that will happen in this. Okay, and then you have to do more work. That's not enough to show minimum distance is 4, right? You have to say that those 3 will not give you 0. I mean, you do a lot of careful work, and then you can show that d equals 4 will work out. Okay, but it's a lot more work than the previous case. Okay. We will do one more notion with finite fields, and then we will move on to these BCH code constructions, which is quite simple. It is very similar to the previous construction that I had. Okay, so it is a nice construction that gives you the minimum distance. But before that, we need just this one more idea from these finite fields. That is the notion of this minimal polynomial. So once we have this notion, we will be ready to jump into the BCH code construction, and then we can finish it off. Okay. So what? So let's say we have FQ, which is Q is a prime power. Okay, so let me say Q equals P power m. So just for some prime p, and FQ is a finite field that has been given to you. Previous question? Yes, go ahead.
That if the entire column is non-zero, you can say that d is 4.
Okay.
But if there is a 0, there might be some other message word which might still correspond to a.
No, but you can find
distance.
3 columns. You can find 3 columns which are 0. That's it. I have a code word whose minimum distance is 3.
For what? For this specific case, it is 3. Okay, but in the general case, it's less than or equal to 3. That's the conclusion that is theoretically valid. Okay. Yeah, there might be something else here which is identical or linearly dependent and all that. You have to check that. Linearly dependent is a little bit more confusing to check in an arbitrary field, right? Binary, it's very easy. You just check if it's identical. The other fields you have to multiply by all powers of alpha. It's a little bit confusing. It's too many possibilities are there. You can't immediately verify. Yeah, d less than or equal to 3 is the only conclusion you can have from this. Okay, so forget about that example. I know that example is causing some intriguing moments to you maybe, but just forget about it. Let's move on. Let's look at minimal polynomials. Okay, and then we'll come back to a very similar construction when we do BCH. At that time, I'll prove to you that minimum distance cannot be 3 in those kind of cases. Okay, so we'll do that. So FQ is the field, and let's say we have written FQ as okay. So as usual, we have a primitive element So, we do 0 1 alpha alpha squared so on alpha to the power q minus 2 alpha power q minus 1 is 1 and then pi of alpha is 0. Pi of alpha is a degree m polynomial with coefficients in fp. So, this belongs to fp alpha degree equal to m. Okay. So, that is the general way of describing fq, and such an alpha is called primitive. I do not know if I defined it formally or not. Such an alpha is called primitive. Okay. It is a primitive element, it is the root of a primitive polynomial. So, it is all the word primitive will show up again and again in these expressions. Okay. Let us say so now the definition for the minimal polynomial. Okay, so let me give you the definition and then I will justify the definition. Okay, so that is much better. Suppose I have a beta belonging to fq, q is p power m. The minimal polynomial of beta is the smallest degree polynomial in fpx. Okay, so that is the main difference with beta as a root. Okay. So, the crucial two things here are this p is very crucial, and then the smallest degree is very crucial. Okay, so, those are the two things that are important in this definition. Okay. First of all, this definition has to make sense. I will tell you why this makes sense soon enough, but anyway, before that let me ask you another question. Instead of p, if I had q here, what will be the answer? Beta itself, beta is a polynomial, beta is a root with beta. If you think of beta as a polynomial, is beta a root of beta? It is not. Okay. So, what is the smallest degree polynomial which has beta as a root? X minus beta. Okay, so, it is the correct answer. Okay. I don't know why everybody is afraid. No constant non-zero polynomial has a root, right? I mean, it's obviously there is nothing, it will not vanish for anything you put in, there is nothing there is there to put in, okay, except for 0. Okay. Of course, I do not allow the 0 polynomial. Okay. So, if you put q instead of p, the answer is trivial, you have a degree 1 answer which is x minus beta. Okay. But you do not want coefficients from fq, you want coefficients only from fp. Okay. So, that is the added thing here which makes the definition more interesting. Okay. So, if you had q itself, then x minus beta would be the answer, there is no other problem. Okay. So, beta itself belongs to fq, I just have it, but I do not have q here, I have p, which is coefficients from fp is only allowed. Okay. So, let us so if you go back to f8 for instance, I have 0 1 alpha alpha square and all that. I want a polynomial for which alpha is a root, but the polynomial should have only binary coefficients, it cannot have non-binary coefficients. Okay. For f8, do you know a polynomial for which alpha is a root? For binary polynomial for which alpha is a root? Okay, let's look at this. Let's look at this a little bit more closely. Okay, so let's look at the example. I had f8, which is 0 1 alpha alpha squared alpha power 3 alpha power 4 alpha power 5 alpha power 6. Okay, what is, do you know a polynomial for which alpha, the primitive polynomial itself is the answer, right. See, remember alpha power 3. So, if you look at the definition of this field, pi of alpha was simply equal to alpha power 3 plus alpha plus 1, and this was equal to 0. Okay. So, one polynomial for which alpha as a root is x cube plus x plus 1, okay, has alpha as root. Okay. So, if you think of f of x equals this is such that f of alpha equals 0. Okay. This is in F8, okay, that is crucial. Okay. Is that okay? All right. So, go back and look at the definition once again. Okay. I said the polynomial is in Fpx and it has beta as a root, and beta is in Fq, which is a larger field which contains Fp inside it as a proper subfield. Okay. Right. Right. I gave you an argument in the middle of last lecture about how there is inside Fp power m there is an Fp sitting inside, which is isomorphic to the Fp that you know exactly, etc. Okay. So, this operation makes sense. It makes sense for beta to be a root of f of this polynomial which has coefficients from Fp. Okay. You can do that computation in the larger field Fq. Okay. Do you understand what I am saying? Does it make some rough sense to what I am saying? So, for instance, if I have a polynomial with rational coefficients, okay, I can think of a complex root for that polynomial. Okay. But you can't say my polynomial has rational coefficients. How will I plug in a complex number? Well, you can say it, but how do we do that? The complexes contain the rationals as a proper subfield. So, you simply do your operations in the complex field. So, you treat each rational number as a complex number with 0 imaginary part and the real part as the rational number itself, and you do the operation. The same thing you would do here. Okay. When I have a polynomial with coefficients from Fp and when I plug in x equals some element of Fq, what will I treat the coefficients as? Not just belonging to Fp, but belonging to that Fp which is inside Fq. I know there is an Fp inside Fq, so I imagine that is what is happening. Okay. It is very similar to plugging in a complex value into a polynomial with rational coefficients, exactly the same way you treat it. Okay. So, that is what is happening here also. Okay. Yes, no, maybe. Okay. So, let us try something here just for fun. So, if you look at this other polynomial, let us say g of x equals x power 3 plus x squared plus 1, okay. I want you to check this, I am sorry, not f, g. Okay. So, this will for sure work out to 0, okay, in F8. Okay, you have to do the computation. Let us try to do it. If I plug in g of alpha power 3, what am I doing? Okay, in the binary field it is a little bit misleading because the coefficients are either 1 or 0. So, you do not have to treat the coefficients as anything at all, you can just plug it in, you get away with it. So, you put x equals alpha power 3, you get what? Alpha power 9 plus alpha power 6 plus 1, and what does that work out to? 0, everybody agrees? Okay. Is it okay? You can go back and look at the list that you had. So, it works out, that is okay. Okay. So, it looks like every element has at least one polynomial for which it is a root, okay, that I know, okay, that seems like it is okay. Okay. So, let us go back and look at this definition once again, but before that, is everybody okay with this? Did you check it? Okay. Okay, let me ask one more question. So, for instance, the elements with alpha in it are a little bit more complicated, but if you look at just 1 for instance or 0, what about 0? what would be the minimal polynomial of 0? X, do not say 0. People said 0. 0 is not allowed as a polynomial. Okay, we will look at only non-zero polynomials when we define minimal polynomial. Okay, x, it is very easy, right? I do not have to even prove it, you know, it clearly has to be x. If you find a linear polynomial, then that has to be the minimal polynomial, it is no problem. Okay, what about 1?
Alpha x plus
X minus
it is very easy. Okay, x minus 1 or x plus 1. Okay, but for the other elements you have to do some more work. Okay, it is not so difficult, not so easy. Okay, right. So that is one thing. But the other thing I want to quickly point out here, okay, before we proceed, maybe I will not point it out here, maybe I will point it out later, but let us go back to this definition, then make sure that this definition makes sense. What are the various things that are needed to make sure that this definition makes sense? Okay, what do I mean by making sense? Okay, I am saying minimal polynomial is the smallest degree polynomial in fpx with beta as a root. So first thing I should show is, I am sorry, I should show us that there are some polynomials in fpx which will have beta as a root. If there are no polynomials, then this does not make any sense, right? Right, I have to show that first before I even define this. I cannot say smallest when I do not even know that there is at least one polynomial which will have beta as a root. Okay, now I will show you a polynomial which will have all the elements of the finite field as its roots. Okay, so there is a polynomial, it is a very simple polynomial which belongs to fpx, okay, and it will have all the roots, all the elements as its roots. Okay, so this is how you go about doing it, and for that, yeah, for that you need some notion of an order. Okay, so I am going to quickly define it, and let us see how it works. Okay, so order of an element, multiplicative order. Okay, so we will only talk about multiplicative order because additive order is quite easy. Okay, so if you have beta belonging to fq, okay, and you look at this sequence beta, beta squared, beta power 3, so on, sorry, so on, can this go on forever? No, because I have a finite number of elements in my field and every power of beta will definitely belong to the field, so it has to repeat somewhere. So there will be a smallest n such that beta power n is equal to 1 and it will have to repeat at 1, it cannot repeat at some other power of beta, then you can show easily that it has to be have a smaller number which was 1. Okay, so it will repeat at 1. Okay, so that is defined, the smallest such n is defined as the order of beta. Okay, so smallest n such that, okay, it's called order of beta such that beta power n is equal to 1. Okay, is this okay? It's fine, right? So I will say simply order. When I say order, it's multiplicative order. Additive order does not, this is very easy. Why is additive order very easy? So if I keep adding beta with itself, beta plus beta, beta plus beta plus beta, when will I get 0? P times beta, well, p times beta is definitely 1 but 0, but that may not be the order, maybe there will be something smaller which will give you 0. Can it give you 0? No? Okay. Alright, so anyway, if you are convinced, that is good. The additive order is not so interesting, the multiplicative order is very interesting. Okay, so order of beta is smallest n such that beta per n is 1. Okay, if beta is primitive, what is the order? Okay, so let us say fq is this, fq is some, okay, so if beta is primitive, implies what? Beta generates the entire field before it comes back to 1. Okay, so order of beta becomes equal to q minus 1. Okay, so beta power q minus 1 is 1. Okay, now this tells you some very easy things about multiplicative order of elements in finite fields. Okay, right. So if I have fq to be 0, 1, alpha, alpha squared, so on till alpha power q minus 2. Okay. I know the order of alpha is q minus 1. Okay. So, this is easy. So, order of alpha q minus 1, and any other beta in fq is of the form alpha power I, right, it is not of any other form. So, all you have to find is order of alpha power I for I is 1, 2, so on till q minus 2. Okay. Right, this is what you have to find, and what can you show that this will be? Okay. Yeah, some kind of GCD has to come in, right. So, it is very easy to see why this has to work out. See, remember, if you have alpha power I raised to the power of order of alpha power I is what? Equal to 1, right. So, basically you get alpha power I times order of alpha power I should be equal to is equal to 1, right, am I right? Okay. So, if you are looking for the smallest such element, some kind of a GCD has to be involved. I can prove this to you quite rigorously if you like. So, it will end up being q minus 1 divided by GCD of I and q minus 1, something like that. Okay. So, I do not know how much detail I want to go into, but you will get some number. Okay, but anyway, I mean, I do not know if I really need to go into the order or anything like that. So, basically I do not even need that. I just want to show you a polynomial which will have all the elements as roots, and clearly that is very easy. I do not even need to do this. Okay. So, alpha power I, all this I do not need. So, basically any element alpha power I raised to the power q minus 1 becomes what? Is basically alpha power q minus 1 raised to the power I, alpha power q minus 1 is 1. So, you simply get 1. Okay. So, I do not think I even need the order, I do not know why I thought about order. Okay. So, this is good enough. Okay. So, alpha power q minus 1 raised to the power I is 1. So, if you look at the polynomial x power q minus 1 minus 1. Okay. So, let us look at the polynomial f of x equals x power q minus 1 minus 1, okay, right. You can easily show for all I equals what, 1, 2, so on till q minus 2, in fact even q minus 1, why not. Okay. F of alpha power I is equal to 0, right. I do not even need order, I do not know why I just suddenly got diverted into order. All you need is basically alpha power q minus 1 is 1. Okay. So, any alpha power I also, when you raise it to the power q minus 1, it becomes 1. Okay. So, that is the only thing you need. Okay. So, your f of alpha power I is 1. So, you can also make a small change, you can simply multiply this by x to get x power q minus x, in which case what will happen? I can start with I can say f of alpha power I is 0 and f of 0 is also 0, right. I am just making f of 0 also as 0. Okay. Remember, this is a polynomial which belongs to fpx. For any p you choose, this belongs to fpx. Okay. All right. So, what did I want to show? Just got these long lectures sometimes can be very tiring. Okay. So, for every element in fq, I wanted to have some polynomial with coefficients from fp for which it will be a root, for which that beta will be a root. Now, here is a polynomial x power q minus x which definitely has beta as a root. Okay. But the question is this the smallest degree polynomial or minimal polynomial with minimal degree? Degree q I can definitely find, there is no problem, but q is seems like such a large number. Do you really need q, or can something smaller work? This is the important question. Okay. alright. So, the definition makes sense, okay. So, that is the main point I want to make here, definition makes sense. Okay. So, let us try and find the smallest degree polynomial. Okay. For that, this notion of conjugates is very useful. Okay. So, conjugates is the next notion which will help us find the minimal polynomial. Okay. So, I will give you the definition and then I will give you an analogy which will help you understand what happens. Okay. So, here is the definition. So, if you have beta belonging to Fq, Q is p power m, the conjugates of beta are basically, you can include beta if you want, not a problem, beta power p, beta power p squared, so on. Okay. Maybe I will include the next one also, beta power p power 3, so on. Okay. So, when I defined order also, I had a sequence like this, it was what, beta, beta square, beta power 3, so on. This is a totally different sequence. Okay. Beta, beta power p, what is this p? P is the characteristic of this field, beta power p square, beta power p power 3, so on. Okay. All right. So, why is this conjugate interesting when I look at minimal polynomial is, this is the reason. Okay. So, why do the conjugates play a role? They play a role because of this region. If you have f of x belonging to fp x and f of beta equals 0, okay, this implies f of beta to the power p power I is also 0. Okay. So, if you have beta as a root of a polynomial with coefficients from fp, what else is also a 0 of that same polynomial? All the conjugates of beta, okay, beta power p squared, beta power p, beta power p power 3, all these things are also roots of that same polynomial. Okay. So, that is the crucial idea, that is the reason why conjugates are important when you look at minimal polynomials. Okay. I will give you an analogy, it is very easy to look at it from an analogy point of view. Okay. So, this real numbers and complex numbers you have dealt with, you have also learned about the complex conjugate. Okay. So, what is the conjugate of a plus ib? Okay. So, for the real numbers contained in the complexes, conjugate of a plus ib is a minus ib. Okay. If I have a polynomial with real coefficients and a plus ib is a root, then what else is also a root? A minus ib is also a root. So, that is the way, that is the fundamental reason, that is the fundamental way to define these conjugates. Okay. So, if you have a larger field and a smaller field inside it and you look at conjugates of that larger field with respect to the smaller field, this is the definition of a polynomial, it should also divide. Okay. So, this is the idea to keep in mind. Okay. So, if you want an analogy, if you do not want an analogy, forget about it, you can come back to this. Okay. So, let me try and prove this to you, it is not too difficult. Okay. So, it is quite easy. So, one thing we saw, so let us say f of x belongs to fpx. So, let us say f of x is f0 plus f1x plus so on till say some fn x to the power n, okay, some n degree, I do not know what it is, but some n degree. Each of these fi's belong to fp. Okay. Remember, this fp is a finite field, okay, and it also has a primitive element. Okay. I did not really prove this, but I also said every finite field, but I already asked you to accept it and you all accepted it. So, now I can use it. Okay. Every finite field has a primitive element. Okay. So, fp also has a primitive element. So, that primitive element raised to the power p minus 1 is going to be 1. Okay. So, that clearly means, you remember fi is f power p, okay, go back to that previous polynomial. So, which means fi is a root of what? X to the power p minus x, right, that is what I showed you before, right. If any element is the root of x bar q minus x. Okay. So, fi is clearly the root of x bar p minus x. So, this basically implies fi power p equals fi. Okay, so this is an important result which we will use. Okay, this is also a very standard result in number theory. Okay, a power p equals a mod p. Okay, it's named after somebody. Anyone knows the name? Yeah, Fermat's little theorem or whatever. Okay, so a power p equals a mod p. Mod, that's a very standard result. So this is what we are recovering here in this case also. Even for fq, we know this is true. Any element in fq raised to the power q gives the same element. It doesn't change. Okay, f by power p. So what I am going to do now is take f of x and raise it to the power p. Okay, if I raise it to the power p, what will happen? It is basically f0 plus f1x plus so on till fn x to the power n. Okay. So the first set of coefficients are first set of terms are very easy to write down. Okay, I will simply take each element, raise it to the power p. Okay, so remember I am just multiplying as p times. It's a very simple multiplication to do. First thing is f0 power p plus f1 power p x to the power of p plus so on till fn power p x to the power of p whole raised to the power n, right. My claim is there are no other terms, okay, right. So if you don't pick the same element and raise it to the power p, every other term will appear a multiple of p times. Okay, this is a thing you can check in binomial. It's very easy to check because p is prime, right. X plus y power p, every p choose I for I not equal to 0 will have p as a factor. P will be a factor in that. The same thing will happen here. Okay, so you can quite easily prove it. I am not going to prove it to you, but no other term will happen here. Okay, think about why that is true, because there are p terms here and you have a p choice in picking one thing if you choose to differ. Okay, so that's the idea. So you will get a p multiple happening once you say you are not picking the same element. Okay, so everything else will go off to 0. Okay, so check this if you like. It's an interesting exercise. Okay, or look up one of your multinomial theorems. There are extensions of the binomial theorem to give you arbitrary formulas for multinomials, and you will see p will be a factor there. Once p is a factor, what happens? It goes to 0. I don't have to worry about it. Okay, so this will be the expression. Okay, now I can keep repeating this. Okay, I can repeat this as many times as I want. Okay, I can do p squared, same thing will result. Okay, but remember what is fi power p? Same as fi itself. So this simply becomes f0 plus f1 x power p plus so on till fn x power p raised to the power n, which you can write in a very smart way as f of x raised to the power p is the same as f substituted with x power p. Okay, so it's a curious little result which is true for finite characteristic fields. It's not true if you don't have a finite characteristic. In real and all, you won't have any such result. Okay, but f of x whole to the power p is the same as f of x power p. Okay, so now can you show if beta is a root, beta power p is also a root? That's all. This equation is the proof of that. You put x equals beta, on the left hand side you have 0, so definitely f of beta power p is also a root. So how do you show f of beta power p squared is also a root? Yeah, let's again put x equals beta power p, you will get beta power p squared, and you have shown it. Okay, so f of beta equals 0 implies f of beta power. Okay, this display driver is dying on me too often, so sorry for that. It's not in my hands literally. Beta power p power I is 0 for I equals 1, 2, so on. Okay. Okay, let's go back and see the example that we had in F8, okay, and convince ourselves that this is true. we're all engineers, so unless we see examples we will never believe something is true, right. Abstract proofs can go wrong. Okay, so let us see an example. Okay, in F8 we had minimal polynomial of alpha. What was the minimal, not minimal polynomial, one of the polynomials which had alpha as a root was f of x equals x power 3 plus x plus 1, f of alpha was 0. Okay, you can check that f of alpha squared will also be 0 and f of alpha power 4 will also be 0. I do not have to check for f of alpha power 8. Why? F of alpha power 8 is very easy to check. Why is that very easy to check? Yeah, it is the same as f of alpha. Okay. Now we have something interesting. Let me see if anyone is noticing anything interesting here. Is anything interesting in what I have written down? Have f of x which is a polynomial in fpx. Clearly it is also a polynomial in fqx or any other f, I mean it does not matter, just some polynomial. Okay, I am treating it as that. Then I am looking in fq, how many roots do I have?
3.
3 roots. Okay, so what should happen? Okay, so f of alpha is 0, then x plus alpha should divide x power 3 plus x plus 1. So x plus alpha squared will also divide x power 3 plus x plus 1 and x plus alpha power 4 will also divide x power 3 plus x plus 1. So what should definitely have happened? X power 3 plus x plus 1 should have definitely been x plus alpha times, well should I say minus alpha or plus alpha? I am doing f8 now. Okay, in general it is minus, I agree with you, but this is f8, so minus is the same as plus. Okay, x plus alpha squared times x plus alpha power 4. This has to be true. Okay, check this. Okay, I think it is good the first time you see it to multiply it out and check that indeed you are getting x power 3 plus x plus 1. Okay, so it is a polynomial of degree 3. It can have at most 3 roots. Okay, so this is true for any field. Okay, in any fx it is true that a polynomial can have at most degree roots. You cannot have more than degree roots. If it has more than degree roots, the polynomial is identically 0. Okay, so that is true for any field. Okay, here I have 3 roots, so clearly it has to be like this. There is no other. I know x power 3 matches, so the form is also very easy to write down. See, the coefficient of x power 3 on both sides is 1. So this is the way to write down. It is an interesting thing to check, but on the face of it you would not think this is true, right. On the right hand side you have all these abstract alphas like you put it, and the left hand side you have only the very real ones. There is no abstraction in that, right. It is true, this is an equality. Not happy?
Too long.
So in a way what is happening here, okay, so you can check this, I will let you check it later. Okay, I want to make a point here which is quite important. Okay, so you take some number, some element and form this product x plus alpha square, x plus alpha power 4, all the conjugates together. What you end up getting a polynomial, you get a polynomial on the left hand side. It has coefficients from the smaller field. Okay, this is true in your real numbers and complex numbers also. You do x minus a into x minus a star, it looks like complex number, but you do not have any complexes in the after the product, right. X squared minus a plus a star becomes simply 2 times real part of a, and then you have plus a star which is actually mod a squared, which is again real. Okay, so these things have obvious extensions in the real, obvious analogies in the real complex side also. Okay, so this is the idea. Okay, same thing is true for the other case also. You can show, for instance, there was another polynomial that I had, right. What was g of x? X power 3 plus x squared plus 1. Then I had g of alpha power 3 is 0, and then you square it, you get g of alpha power 6 is 0. You square alpha power 6, what do you get? Alpha power 12, alpha power 12 is what? Alpha power 5, because alpha power 7 is 1, no. So g of alpha power 5 is also 0. So clearly what should be x power 3 plus x squared plus 1? X plus alpha power 3, x plus alpha power 5, x plus alpha power 6. Okay. Okay. Now I want to claim that the minimal polynomial of alpha is actually x power 3 plus x plus 1. Okay. How would I prove something like that? What is involved in proving something like that? Yeah, see if alpha is the root of a polynomial from f2x, okay, so I can as well say this is f2, right? Yeah, right, see. Yeah, so if alpha is the root of some polynomial in f2x, surely alpha square and alpha power 4 are also roots of that same polynomial. So there is no way the minimal polynomial of alpha can have degree less than 3, it will have degree at least 3, and I have one polynomial here which degree equal to 3. So clearly this should be the minimal polynomial of alpha. Okay, same thing is true here. Minimal polynomial of alpha power 3 has to be this for precisely the same reason. Okay, so similarly this is minimal polynomial for alpha power 3. Okay, let me ask you a couple of questions with simple answers which will maybe make you think. What is the minimal polynomial of alpha squared? Okay, same as this. Okay, so one thing that was very obvious is all the conjugates will have the same minimal polynomial, it has to be the same. Okay, so the minimal polynomial of alpha, alpha square and alpha power 4 will all be x power 3 plus x plus 1, because they are all conjugates. Wherever you start, if you keep on squaring, you will get the other terms. Okay, so the minimal polynomial of alpha power 3, alpha power 5 and alpha power 6 is x power 3 plus x squared plus 1. What is the minimal polynomial of 1? X plus 1. Okay. All right. So let me show you one more impressive fact. I will impress you with one more fact. Okay. So I told you something about x power q minus x. Okay. In this case, x power 8 minus x. Okay. The roots are what? All the elements of f8. How many elements do I have in f8? 8. So what should happen now? Okay, I have a polynomial of degree 8 and it has 8 roots. So what should x power 8 plus x be? Minus x or plus x? Okay, so I am all doing in f8. Okay, so it is all in f8. So minus plus does not matter. Okay, what should x power 8 plus x be? Product of, let us say, some a or I do not know, beta and we have to use Greek, no, I mean it is not right to say something non-Greek belongs to a finite field. Okay, so beta and f8 x plus beta. Okay, so look at what is happening here, it is very interesting. So I put beta equals 0, I get x. Okay, that is one factor. Put beta equals 1, I get x plus 1. Then I put beta equals alpha, alpha square, alpha power 4. I will multiply those three together. What will I get? Alpha power 3 plus, I am sorry, x power 3 plus x plus 1. Then I have alpha power 3, alpha power 5 and alpha power 6. I multiply those three terms together, I will get x power 3 plus x squared plus 1. Okay, so this is a factorization which works only modulo 2. Okay, so if we do not have modulo 2, this factorization will not make sense. Of course, it is all in f2 and f8 and all that. It is important. Okay. Surprising, impressive, no? Nobody seems that impressed. I don't know. Okay. So now let me just quickly formalize a couple of these facts. The first one is conjugates have same minimal polynomial. Okay, you can prove it. I don't want to prove it and I will write it down. It's just a question of writing it down. Have same minimal polynomial. This is true in general. The next fact, which I did not state anywhere, but it is also easy to prove, is that the minimal polynomials are irreducible. How do you quickly show that the minimal polynomials have to be irreducible? If they are not irreducible, what will happen? You can write it as a factor of two other things, and your element has to be the root of one or the other, which would have a strictly smaller degree, and that violates your minimality assumption on the definition of the minimal polynomial. Okay, so that is the way you prove it. It can be written down. You can show it is irreducible. So the minimal polynomials will have to be irreducible, and the conjugates have same minimal polynomial. In the next statement, which is interesting to show, is the minimal polynomial of beta equals product of, let us say, gamma belonging to conjugates of beta x minus gamma equals, I have said put an equality. Okay. So this is a key result. Which needs proof. I will prove it sometime in the next lecture. I will give you a very simple high level overview kind of proof. There are also very rigorous ways of showing it. Okay. Basically, after a lot of examples and some pseudo proofs, we have come to the key result, which is the minimal polynomial of an element in a finite field can be found very easily. Okay, what do? You first find all the conjugates of that particular element. Okay, so how do you find the conjugates? You list beta, beta power p square till you get a repetition. The moment you get a repetition, you have to stop. You cannot keep on going. Okay, so once you do that, you get the list of conjugates. And then it turns out you multiply x minus those conjugates, you end up getting the minimal polynomial. What does it mean? It means in particular that this polynomial has coefficients from fp. Okay. So that is the only non-trivial thing to prove here. Once you show that the coefficients of this polynomial on the right hand side is from fp, you are done, because that has degree equal to the number of conjugates, and that has to be the minimal polynomial. There is nothing more to prove beyond that. The only thing is, how do you show that this guy has coefficients from fp? It is a little bit non-trivial. Somebody else said that before me. Okay. The idea is to show, you have to basically, what you have to do is you have to raise this polynomial to the power p and show that you get the coefficients unchanged and x becomes x power p roughly. If you show something like that, then you will get the answer. Okay. So then it means that the coefficients when raised to the power p remain unchanged, and that means they are in fp. Okay. I haven't shown all those things, but that's the rough proof we will do sometime in the next class. Okay. So think about it, it is very interesting. Another thing you should try is go to F16. F16 list conjugates and find minimal polynomials. You can do this, right? You have all the element tools to do it. You make the table, take one element, find all its conjugates, do x plus that, multiply. You from the table you can do everything, right? You do everything, you can find all the minimal polynomials very easily. Or if you want a simpler method, simply go to MATLAB and ask it to find minimal polynomials. That is the easier way of doing the whole problem, but if you want to do it by hand for the first time, I will encourage you to do it. Okay, that is it. If you are done, we will meet tomorrow.